Today I would like to give you an overview on microstructure, mechanical behavior and fracture of steels proceed with power fusion additive manufacture. So just let me introduce myself. I'm Kahlert from the Institute of Mechanical Engineering from Professor Thomas Niedorf in the beautiful castle. And we will kind to see you there if you want to not to be stuck at train station Castle del Seu, and feel free to ask us for a laboratory view or something like this. To come back to our topic today, I will start with a small introduction of the PBF process. Then I will come to the microstructure, the potential and cyclic loading of the steel AISI H13, and I will finish with some prospects for possible applications of this steel. So the powder bed fusion, also known in the electron beam state, is the electron beam melting. It is a typical powder bed fusion process. Starts with a layering of powder, then raking, and then there is a step which makes it different to the SLM process, the preheating. This step is necessary to get in higher the conductivity of the powder for preventing powder blast in the process. The whole process is near 1000 degrees, up to 10,000 degrees, and the electron beam is the source of the melting of the ceramic melting process. After this, the table is lowering and the process is repeated until the part is finished. So in this investigation, we used the powder of the steel AIS13, which were in a gas atomized state from a powder size distribution of 45 to 106 micrometers. For processing, we preheat the platform to the target temperature of 920 degrees and holding it for 30 minutes to sintering the powder under the base plate for hiring the electron conductivity. In the pre-sintering process, we used these shown parameters, and for melting, we just verified the power of the laser beam, which results in 3 different volume energies. So when we look at the optical microscopy of the specimen, which are produced with these 3 kinds of volume energies, we can see 3 crack-free specimens, but with lack of fusion at the lowest volume energy. But at the higher volume energies, there are no cracks and no lack of fusion in this specimen. Coming to the microstructure, we can see a fine-grained microstructure and a formation of a small-scale structure which is elongated in clustering parallel to the building direction, which are indicated in C and might be related to the solidification of the apparent gamma rays. When we look at the EVSD images, we can see a fine needle-like microstructure which are predominantly anisotropic and lightly elongated in the build direction. When we look at the hardness, we can see that there are no inference of the process parameters, but there are influence of the build height. In the uppermost layers, there are a higher hardness than in the downper layers, and this comes from some annealing processes in the downward layers and some like quenching in the upper layers, resulting in this hardness. Thanks. Also, the line measurements show these results. So when we look at the tensile test results, we can see that there are a big difference in the elongation and fracture at the lowest volume energy, because there are some lack of fusion defects lowering these elongation and fracture dramatically. But we also see the relatively high elongation and fracture if the specimen are fully dense. Yeah, and looking at the fracture surfaces, you can see that there are lack of fusion defects also in the fracture surfaces, which are the reason why the results in a weak mechanical behavior and a low elongation of fracture. We also doesn't see any lack of fusion defects in the other specimens with a high density, also in the optical microscopy. So what happens when we do some heat treatment to this state? We compared the PBF EB specimen with the conventional specimen, and we can see that quenching dramatically higher the state also in the conventional compared to the PBF state. But what you can really see is that when we temper one or two times our PBF EB specimen and our conventional one, which is a hot rolled material of the conventional processing step, with the curves fitting together and are completely the same. That's what we can see in here, is that we can use the full potential of additive manufacturing in contour, in near net shape, or we can build some cooling channels in tools or something like this. We can use the full potential, and we have still the same material as we know from the conventional process steps. We also do some fatigue tests, and we see here some Euler curves which are compares a PBF EB with a PBF LB stage, and we also see that lack of fusion defects dramatically reduce the cycles to failure and also the fatigue strength of the specimen. And to give some possible applications, we do a joint venture with the Center of Lightweight and Casting. Here we increase the heat transfer and cooling channels with imprinted statical mixers, and we do some thermography measurements, and we can see that also in the simulation and in the real tests we could increase the heat transfer by hiring the turbulence with our mixers in the cooling channels. So possible another application is to imprint some sensors into our material to measure the temperature or the pressure in there, and we do some live measurements while printing, and it's pretty cool to do this. So let me conclude by saying in the PBF EB process, quenching of the outermost structural layers and tempering of the underlying layers occurs, resulting in increased hardness in the uppermost layers. PBF process AISI H13 shows good microstructure and mechanical properties under quasi-static and cyclic loading, provided that material has no structural defects. Using AISI H13, the advantages of additive manufacturing in terms of geometry freedom and integrated sensor technologies can be also used in technical applications. So, thanks for your attention. Are there any